Welcome to the Harper Classroom series of instructional videos. I'm Dr. Harper. This video is on Stochastic Inventory Theory Part 1, Statistical Safety Stock with Excel. This is Part 1 in a 4-part series in Stochastic Inventory Theory. The Statistical Safety Stock is part of the reorder point in a continuous review system. As an introduction, the inventory can be increased by acquiring items from the supplier, which is dependent on the lead time. The inventory can be decreased by distributing items to the customer, which is dependent on the demand. The inventory policy answers the question when to order and how much to order from the supplier. When the demand and lead time are constant, the when to order is answered by the reorder point, which is demand times lead time plus safety stock. The order quantity answers the question how much to order, demand times inventory period. In this video, I will introduce a generalized stochastic ROP equation and derive it. And then from that equation, I will allow the demand to be stochastic following a normal distribution and derive this equation and then apply it. And then allow the demand and the lead time to be stochastic following a normal distribution, derive the equation, and then apply it. So as I derive these equations, I will first introduce the concept, then the derivation of the equations, and then the mechanics, which is working a problem. There are two sets of background information for this video I would like to cover. The first is transformations between the normal random variables d, which is demand, and z, the standard normal. The second is the expectation and variance relationships. Let's start with the transformations. Suppose our demand is a random variable, d, which follows a normal distribution. Well, for stochastic demand, where stochastic means random, d follows n, which is normal, with a mean of mu and a variance of sigma squared, where the mean of d is the expectation of d, or mu of d, and the variance of d is v of d, where v stands for variance, or sigma squared d, and the standard deviation is the square root of the variance. There's some language here. The d is the random variable because it varies along this axis, and mu is the mean. Well, that's a constant, and it's a constant mean of the distribution. The d sub alpha is also a constant, but it's a random variate. This is a random variable, this is a random variate, and the variate is a value of the variable. The subscript alpha refers to the area under the curve, which is the probability alpha. For this video, I will use the mean to be 539, and the variance is 6724. Now, if I want to transform d to the standard normal z, I use this relationship. I subtract the mean from the demand, random variate, which is the location parameter, and that relocates it to 0. I divide by the standard deviation, which is the scale parameter, and I scale the variance to a variance of 1. And so that's a transformation to the z random variable. So we've standardized it to a mean of 0 and a variance of 1. Now, if I want to transform back, I just solve this equation for d, and I have a relationship, a transformation from z back to the d. Now, for the expectation and variance relationships, first, the expectation of x is referred to as the mean mu. That's by definition. The expectation of x is also a linear operator. Where a and b are constants, ax plus b, the expectation of that linear combination of x, a as a constant will come out, and b, the expectation of a constant, is just a constant. And so the expectation of ax times plus b is just a times the expectation of x plus b. Now the variance of x is defined as sigma squared. And so if you have a variance of the sum of the x's, where the x's are IID, which IID refers to independent, identically distributed, for example, normally distributed, then the variance of the sum of the x's is the same as the sum of the variance of the x's. The variance of x is also defined as the expectation of x minus expectation of x quantity squared, where the expectation of x is the mean. So x minus the mean is really the error. So if I square the error and then take the expectation of the error, that's called the mean of the squared error. If I expand this and square it, and then the expectation is a linear operator, pass it through, then notice I have the expectation of x squared minus 2 times the expectation of x, and the expectation of x is just a constant. So I can combine these terms, collect the terms, and then I have the variance, which is sigma squared equals the expectation of x squared minus mu squared, or the expectation of x squared is the sum of the variance and the square of the mean. And we'll use these identities in the derivations in this video. Now, statistical safety stock, reorder point in a continuous review system. First, concept. So let's start with constant demand. So as we distribute items to our customer to satisfy demand, our inventory level drops. At this point, we place an order. And we place an order, that's ROP. And then we receive our order right here. The difference between when we place an order and receive an order is our lead time. But during that lead time, we're going to have demand. So our demand during our lead time equals our demand rate times our lead time. So this demand during lead time represents our ROP. So when our inventory level drops to ROP, we place our order. But during that lead time, if our demand is greater than expected, then we're not going to have inventory to satisfy that demand. And that's called stock out. Stock out is the same as unmet demand during a lead time, and that happens when the demand during the lead time is greater than the ROP. Well, to guard against stock out, we carry something called safety stock. So we carry safety stock all year long to guard against stock out. But if we're carrying safety stock, that increases our inventory. So that will be added to our ROP. So now our ROP is our demand during the lead time plus our safety stock. So safety stock guards against stock out, which implies our ROP is going to be the demand during lead time plus our safety stock. But safety stock guards against stock out because of uncertainty of demand during lead time d sub LT. And so this uncertainty is where we move into stochastic inventory theory. We'll look at the uncertainty by modeling it with a normal distribution. So for stochastic demand following a normal distribution with a mean, mu, and variance sigma squared, our inventory level no longer is a straight line, it varies randomly. At this point, at ROP, we place an order and then we receive an order, and our lead time is the difference between placing and receiving an order. But we still have demand during lead time and safety stock, but this time our demand during lead time is the expectation of our demand during lead time, because demand now is a random variable. And our safety stock, sub alpha, where alpha is the stock out level. So we can express ROP as the expectation of our demand during lead time, plus our safety stock with a stock out level of alpha. The probability of stock out is a probability that our demand during lead time is greater than the ROP, and that's expressed as an alpha, which is called the stock out level. The stock out level can be used to determine the safety stock. And when it is, the safety stock is called statistical safety stock, which is the subject of this video. So let's look at the derivation of the equations. In the development, the first thing I will look at is take the ROP equation and derive the generalized stochastic ROP equation. First, we start with the ROP expression and the stock out level, and then we substitute the ROP equation in for the stock out level probability. And then the normal transformation. Since my random variable is my demand during lead time, if I subtract the expectation of the demand during lead time from both sides, divide by the square root of the variance of the demand during lead time from both sides, then the left-hand side here will be a z, a standard normal. And the right-hand side will be this expression. I'll subtract out the expectations and just have the safety stock sub alpha divided by the square root of the variance of the demand during lead time. But I know from the standard normal that the probability that z is greater than z of alpha equals alpha. So these two are equivalent. The only difference between these equations is z of alpha and this expression. So I can set these two random variates equal to one another, solve for my safety stock, and there I have my expression. So I take my ROP equation down, I substitute in my safety stock, and that derives the generalized stochastic ROP equation. So now let me take this generalized stochastic ROP equation and derive the ROP equation for the stochastic demand, where the demand follows a normal distribution. Essentially, I'll show that the expectation of the demand during lead time is that expression, and the variance is that expression. Let's start with the mean, the expectation of the demand. Well, the demand during lead time is the sum of the demand, I equals 1, to the lead time. I want to show that the expectation of that demand during lead time is mu of d times LT. We take the expectation of the demand during lead time. Since the lead time is a constant and the demand is a random variable, and expectation is a linear operator, the expectation of the sum of the demand is the sum of the expectation of the demands, and the expectation of the demand is mu of d. I sum that constant LT times, and that equals mu of d times LT, and there's the expression. Next, the variance. I want to show that the variance of the demand during LT equals the variance of the demand times the lead time. Well, the variance of the sum of the demand during lead time, if my lead time is a constant, and it is the sum of the variances. And the variance of my demand is sigma squared. Since I'm summing this constant LT times, it's got to be sigma squared times LT. And there's my expression. Mechanics. Let's solve a problem. Suppose we have a weekly stochastic demand with a mean of 539 and a variance of 6724. When to order, here's our ROP equation. And how much to order, here's our lot size equation. Given, our inventory period is 1.5 weeks with a lead time of 0.2 weeks. Our stockout level is 10%, which results in a service level of 90%. Our Z value is 1.282, which we'll solve with Excel in a minute. When to order, I bring down the ROP, and then I substitute. The mean is 539. The lead time is 0.2. Z is approximately 1.282 times the square root of the variance, which is 6724, times the lead time, 0.2. Doing the arithmetic, the ROP is approximately 155. How much to order? I bring down the equation. The mean is 539, and the inventory period is 1.5 weeks. So the lot size is approximately 809. So our inventory policy is 155, 809. But notice all the values are in weeks, so they can be used directly in the equation. But if the values have a mixture of time units, then they all have to be converted to the same time units in order for the equations to work. And there's a video on time conversions in the Harper classroom. So now, let's see how to solve this with Excel. So let's type in our values. Our demand mean is 539. Our variance is 6724. And our lead time is 0.2. Inventory period is 1.5 weeks, and our alpha is 0.1. Now our Z value is equal to the normal distribution, standard, inverse. And since our alpha, which is our stockout level, is 0.1, 1 minus alpha will be our service level, and that's approximately 1.282. Now our ROP, from our equation up here, it's equal to our mean times our lead time plus our Z value times the square root of our variance times the lead time. And so there's our equation. Return, and I have 154.79 rounded up to 155. Our lot size equation is given up here, equals the mean of our demand times our inventory period of 1.5. And there's our equation. 808.5 rounded up to 809, and that's how you solve this with Excel. So now let's look at the derivation of the second ROP equation, which is the demand and the lead time both are stochastic and follow a normal distribution. Essentially, I'll show that the expectation of the demand during lead time is that expression, and the variance is that expression. So let's start with the expectation of the demand during lead time. So here's the demand during lead time, but this time the demand and the lead time are both random variables. I'm going to show that the expectation of my demand during lead time is the product of the means. I start with the expectation of the demand during lead time. Well, the conventional approach, since I have two random variables, is condition on the lead time, so the lead time becomes a constant, and then takes the expectation of the demand. Now, whatever that expression is, let the lead time be the random variable, and then take the expectation of the lead time. So if I let the lead time then equal my constant n, now I have the sum of my random variable over a constant n. Well, since my expectation is a linear operator, the expectation of the sum of the demand is the sum of the expectations of the demand. But now I have the expectation of the demand given the lead time of n over a constant n, and that's going to be the sum of the mean mu of d, which is a constant. Now lead time now becomes a random variable. Well, since this is a constant, the sum of a constant is just a lead time times the mean. Now the expectation of the lead time then becomes just the mean of the lead time, and there's my expression. So now let's derive the variance of the demand during lead time as this expression. So if the demand over lead time is the sum of the demand, where the lead time and the demand both are random variables, show that the variance of the demand over lead time is given by this expression, which is the mean of the lead time, the mean of the demand squared, and the variance of lead time and the variance of the demand. So let's take this expression, move it up here, and start with the variance of the sum of the demand over the lead time. So the variance of a random variable is given as the expectation of that random variable squared minus expectation of the random variable quantity squared. I'm leaving off the I equals 1, but it's still there. So this is from the relationships of the expectation and the variance. So since we have two random variables here, we condition on lead time, let that be a constant, and take the expectation relative to d of this expression where lead time is a constant. Then whatever that expression is, take the expectation of that relative to the lead time. Now this expression, the expectation of the demand over lead time, where both are random variables, we've just done that. And we've shown that that equals the product of the means. So we'll let the lead time be the constant n, and we take this expression and we bring it up. Now the expectation of a random variable squared is the same as the variance of that random variable plus the expectation of the random variable quantity squared, again from the relationships. And all of that is going to be the expectation relative to the lead time. But the lead time is a constant here until we take the expectation of it. But this is the variance of the demand, and this is the expectation of the demand. We bring this expression up. Since the expectation of lead time is a linear operator, then we pass it through. But now the variance of the sum of the demand is the sum of the variances, and the expectation of the sum of the demand is the sum of the expectations. Well, the variances are the same as sigma squared, and the expectation is the same as the mu. Now we take the expectation with respect to the lead time of these values when we let n now become a random variable. So we bring this up, we let n now be a random variable LT. The expectation of the lead time is just going to be the mean of the lead time. But here we have the lead time squared. And so we bring out the mean of the demand squared times the expectation of lead time squared. We bring that expression up. Again, from the relationship of the expectations, the expectation of lead time squared is the variance of the lead time plus the mean of the lead time squared. We can expand the terms. These two terms cancel out. And what we're left with is our result. Mechanics. Let's solve a problem. Suppose I had a weekly stochastic demand normally distributed with a mean and variance, and a weekly stochastic lead time normally distributed with a mean and variance. Here's our ROP equation and a lot size equation. Given the inventory period is 1.5 weeks, stock out level is 10%, resulting in a service level of 90%, and a z value of 1.282 approximately, and the Excel equation, which we'll derive in a minute. Let me copy down the ROP equation and substitute. The mean of the demand and lead time are 539 and 0.2. Z value is 1.282. Square root of the mean of the lead time is 0.2. The variance of the demand is 67.24. The mean of the demand is 539 squared, and the variance of the lead time is 0.0625. Doing the arithmetic, my ROP is approximately 287. Now, the lot size. I bring down the lot size equation. The mean of the demand is 539 times my inventory period of 1.5 weeks, which is approximately 809. So my inventory policy is 287,809. But let me point out that all these values are in weeks. And if there's a mixture of time units, they all have to be converted to the same time units for these equations to work. And again, there's a video on time conversions in the Harper classroom. Now, let's see how this works in Excel. So let's type in our values. Our demand mean is 539. Our variance is 67.24. Our lead time mean is 0.2. And our lead time variance is 0.0625. Inventory period is 1.5 weeks, and our alpha is 0.1. Now for Z, that's going to be the normal, standard, inverse, and this is going to be 1 minus our alpha. Since alpha is our stock out level, 1 minus alpha would be our service level. And there's the approximate 1.282. Now, ROP. ROP is given up here in the equation, which is equal to the product of the means, 539 times 0.2, plus our Z value, times the square root of our mean of our lead time, times the variance of our demand, plus the mean of our demand squared times the variance of our lead time. And so there's the equation. The lot size is given by the equation up here, which is equal to the mean times the inventory period. And so we can raise this up and we can see that the ROP is 286.7 rounded to 287, 808.5 rounded to 809, and that's how you solve this in Excel. So let's look at a comparison of these inventory policies. When our demand and lead time were constant, with a safety stock of 0, our ROP was 108 and our lot size was 809. But when we introduced stochastic demand with a stock out level of 10%, our ROP went up to 155 because of the statistical safety stock, but our lot size stayed at 809. When we introduced stochastic lead time in addition to stochastic demand, with the same stock out level of 10%, our ROP increased again because of statistical safety stock, but our lot size stayed at 809. So the implication is that when you have uncertainty, as that uncertainty increases, you address that uncertainty with your statistical safety stock in your ROP, not your lot size. So the understanding of statistical safety stock is important to address the inventory policy the right way. This is Part 1, Statistical Safety Stock, which is the reorder point in a continuous review system. Part 4, which I call the Excel workshop, I will solve Part 1, 2, and 3, starting from raw data. With this ends the video Stochastic Inventory Theory, Part 1, Statistical Safety Stock with Excel. I'm Dr. Harper. I hope this helps. Thanks for watching.